So what were we doing yesterday? Just quick recap. So we were looking at the design of this power supply, and the motivation was to design the various components that actually go into this power supply, right? So we looked at many of the components, and then we were looking at this example where we wanted a 12 volt 5% ripple 10 milliamp charger or 10 milliamp power supply, right? And we came up with some analysis, and I left you where we were discussing about what the rating of the diode should be. All right. So how many of you finished this thing to calculate what were we trying to find out? I wanted to find out what is ICP. How many found out what ICP is? What is ICP? Okay. What? Just a minute. Yeah. Okay. So, okay, we'll just go do it here. I don't know where it's disappeared. That paper's flown away. All right. So we have delta T as this. No confusion in delta T, right? Then what should one do? Go back here to this particular expression and this particular expression, right? So you will have that C into what is this VPPR? VPPR itself is Vp into T by, tell me, RLC anything else? No root 3 and all that, right? Because this is a peak to peak ripple. Will be equal to half into ICP into this quantity delta T, and delta T is 1 by under 2T by RLC, right? So how do you simplify this? You want TP from here, right? So your capacitance. What is Vp by R? That is your IL, right here. P by RL is your I. So this is nothing but I. Okay. So you get, you will so you will get IL into T is equal to half ICP. So I'll multiply omega on the side, okay, and left with this quantity of 2T by RLC. And what is omega in 2 pi, right? Omega is, or T is 2 pi by omega. So omega into T is 2 pi, right? So this will come to 2 times, and there's a 2, so 2 into pi into IL square root of RC by 2T. If you take this T inside, this would be equal, just to simplify this, if I keep like a pi, right, pi under root of RLC. So this will be 4, go inside 16, divided by 2, it will be 8, right? 8 times RLC divided by T, the whole thing by IL. Hope I am right in that. Somewhere the paper where I written this down has disappeared. So I might be off by some factors. Be careful. Okay. Interesting. Okay. Okay. So your total, the total is given by two terms. The first term itself is this term, second term is that term, correct? So going back, the total is given by your IL to I under of 8 RLC by T, which is IL into 1 plus pi underscore of under root of RLC by T. Okay. Now for the values that you have so far, can you quickly tell me what is this quantity? What is this? This pi into the root of. So can you see that it is significantly larger than 1? Because the whole definitions, whole exercise started with RLC being very large, right? You started with RLC being very large, then you RLC is very large compared to T. So even if you took say 10 times, right? Took RLC to be 10 times T, or take 12 times, because 12 into 8 is roughly 100. So if you took RLC to 12 times T, this thing will be root of 100, which will be 10. 10 into pi will be around 30, right? So this quantity, because of the current, will be about 20 to 30 times larger than the current that is flowing through your load. Right? So it's something you have to worry about. So can you tell exactly what is it? I expect it in the ballpark of 20 to 30. For just take RL equal to how much? 12. How was RL? RL was 0.2 K. C was roughly 200 microfarads, and T was 20 seconds. Why is it taking so long? Around 12. It may be also. I don't know. Okay, what was I telling you to find? 40? 9.6 pi. Okay, two different answers. Why is it getting different answers? Okay, the quantity I want you to calculate is pi into under root of A into was R what 1.2 K into 192 microfarad by 20 second. That is 20 seconds, right? Somebody else confirm. What's everyone doing? People have all gone to sleep. 31. Completely different. 30, that is into pi, including the pi. That sounds okay. 30.15. Do other get this number? Okay, 30 is there, right? So the initial thing when I did very crude calculation also came to roughly the same thing, right? Because I said RL into C about 12 times T. 12 into 8 is 100. Root of 100 is 10. 10 into pi, around 30. Right? Not bad. So basically, the current through the device is 30. So this is the full current itself will be, okay, assume this is 30. So 31 times IL, and I was milliamps. Right? And that is 300 milliamps. So 0.3 amps. Okay. So this particular number has a name. This is called the peak repetitive current rating. It's called the peak repetitive current rating because this current is now going through the device continuously, right? Every time this device charges, you have a peak current coming to whatever we calculated through the device, and there always the IL which is flowing through the load, right? So the current through the diode reaches a peak every time cycle, every one cycle, right? For this particular, for the full wave, for the half wave, every one cycle it reaches a peak, and that is this current of 0.3 amp. So what I like you to do, okay, is to go and look up, say, the data sheet for two particular diodes. Okay? There is one diode which is called 1N448. Okay. What I want you to do is to go have a look at both the diodes and then tell me which of these diodes is more suitable for this application. One is the 1N448. The diode has a number 1N4000. Okay, there is a diode which is 1N4000. Look at the data sheets of these devices and justify it as to which of these devices is more suitable for the application that we have. Okay, so of devices, some of them are small signal diodes. Some of these diodes are power diodes. So you can have a look. That book, Horowitz and Hill, is a book to get this kind of information. Okay. So with this, basically, you all the design or the specifications of all these currents. There is one other specification which is that what is the amount of current which is flowing through the transformer, right? So that will also tell you as to what is the thickness of the wire that is required to wind the transformer. So when you buy a transformer, right? If now the current rating is 0.3 amps, peak repetitive current rate 0.3 amps, you have to keep this in mind and see how this, because effectively this current coming from the transformer, right? So the transformer, if you did not worry about the charging of the capacitor, you could have gotten away with a transformer which had about 10 milliamps. So maybe 50 milliamps of rating for the transformer would have been good enough. You give a margin of 5 or 10. But now you should keep in mind that every one period you have this peak current which is flowing, and so you should be while selecting the transformer also. Okay? So making a robust power supply actually and looking at a theoretical model of a power supply are very different. And as engineers, one should be comfortable in making a power supply, right? If nothing else, if you don't build a circuit in your 4 years of engineering, you should at least have built a power supply on a PCB and then driven something in that power supply. It's a good exercise for you to do, right? So maybe in the second half of the CAD lab, maybe we might make this depending on what person decides. Okay, so that is with respect to half wave rectifier. Now we'll just introduce what the wave rectifier does, okay, and then one can go through a similar analysis, but I am not do that, right? You are comfortable doing that. So, circuit that we have already, yes, Ankit. Many diodes have a number starting as 1, and then you have the subsequent. So, for example, many transistors start with the number 2n. So, 2n2222 is a very popular transistor. Okay. It's just right. 2n2n05 is another popular transistor. The 2n2222 is a small signal NPN transistor. Its sister is the 2n2905, which is a PNP transistor, both having similar kind of beta. Like in the previous class, in the previous semester, you would have used, no, you used transistor also. Yes, you used the BC, not 182. You used the B77. That was also a PNP transistor. The B177 is very similar. The performance very similar to the 2n2905, and corresponding NPN in that BC series is a transistor named BC107. So this is just an aside. So typically NPN, NP, you have BC17, not use the BC107. The PNP is the BC177 you used, and there's a 2n2222 and there's a 2n295. Okay. So if one looks at the full wave rectifier, we looked already at one kind of full wave rectifier, and that was a full wave rectifier with a center tap transformer, right? So I am not going to go through of this because that will be very repetitive compared to what we already have done, but it will be instructive for you to do it, because there are, a nice question that one can ask in a quiz is calculate, for example, what is the peak repetitive current rating of diode with the full wave rectifier, right? Whatever we have done for half wave rectifier, do it for the full wave rectifier, right? So what did we say? We said that you have a transformer with a winding ratio of n:2. Okay, the center tap I ground here, correct? Then I have one diode which will conduct the forward direction. I have another diode which will conduct it will also conduct in it will conduct in the negative cycle. Sorry, this diode conducts in the positive half cycle. Diode conducts in the negative half cycle. Both of them drive a load. So far we had only put the resistor, right? And I have drawn it very resistively. So we take across this resistor, I put a capacitor. Okay. So it's going to be very similar to the circuit that we had already studied, right? You will have current like that. The voltage. So this voltage itself going to be Vp sin t, which means have the voltage across the half would be Vp by n sin omega t. This part figure I can't, but in the next figure I will. Thank you. So what will happen now? Can you draw the output here? How will the output look? First thing is I have the voltage. So let me say I want the volt cross capacitor. This is minus and this plus, and I am going to look at the voltage VC. sorry, is that right? Yeah. Okay. So first thing is that if you did not have the capacitor, how will the output voltage look? Without the capacitor, the positive will come through and then the negative, you will negative also, right? So you will get that. This without the capacitor. That's what we had already seen when we first came across this circuit. Now once capacitor is there, and assume again that you have chosen RLC significantly larger than T or T by 2, right? What now the output to be? Right? Basically, it will start from here and then charge linearly, right? Go up again, discharge linearly, go up again, linearly, go up again, like that. Okay, so it's very similar to the previous circuit that we had here. One difference is that this linear fall is now be for a time period roughly T by 2, sorry. That is this time from here to here, that's the period of charge, right? That's the discharge period, and the period is approximately T by 2. So you can go ahead and find out the various quantities that what are the quantities that you will need. Just to write it out here, you should find out what is V. So work all these things. What is the V? P to P equal VPPR. Then find out what is the V ripple, which is the RMS quantity, RMS equivalent VPPR. Then should find out the ripple factor, right? Then what else? You should have the various rings, right? So you should have the rating for the capacitor. So for the capacitor, so you have it for the capacitor voltage. Is this big enough, Pratish? Is big enough? So capacitor, then yes, what is the repetitive peak repetitive current, the diode. Okay, then correct, peak in voltage of the diode, basically quantities that calculated so far. Okay, now you can do all of that. They will very simple. Some will be worse, some will be better, and know which is worse, which is better, because those are things we ask you. Okay, now we'll just do one extension to this and then we can close. Basically, in this particular circuit, what is the to its functioning? Okay, no, in terms of infrastructure, what is the what is important? Yes, right. So the most important thing here is the center tap transformer. And many stations, a center transformer is not always available. Okay. Okay. So can you come up with a circuit which is a full wave rectifier but does not use the center tap transformer? Yes, right. So you might have come across this in school. Those who have done electronics, you might have come across this. So it's actually quite straightforward, right? So this is the last of the power supply part, which is the full wave rectifier. Out. Center transformer. So anyone remember how that works? So let me start first with the transformer itself. Have the transformer, right? The second straightforward circuit, there is no center tapping. So one possibility is, let's first just take the positive cycle. Okay. So to drive the positive half cycle, let me assume that I have a diode. Okay, and let me connect a load, and then again I need to close this. So let me connect another diode this way. Okay, and as in, this load is not just you can have an R, but you need to have a cap across this, smoothen out the ripple. So you can, and you know how to choose the R and C to get what. Okay, so in the positive half cycle, that is when this, let me call, so let me say that is the dot, and this is also the dot. So say when the dot, and let me mark this as cross and this is cross. So when V dot is greater than V cross, it is going to flow like that, the red color. Okay, so I draw the current flow direction here. Then what is when, for example, V dot becomes less than V. So to see where exactly this is happening, right. So in this region you have your right, in that red region V dot is greater than V cross, right, and in this region, in the green region, it is less than V cross, right. So the bottom part is more positive than the top part. So what do you want in this at the time, right? The current through the diode should still be the same direction, right? You want to flow through the diode in the same direction. So one way of doing that is, let me just draw these two diodes and then you can see what's happening. Okay. So let me draw that in black, and then I'll draw the current direction in red, in green. So assume I have another pair of diodes connected. So I connect this to this. Okay. So the current will go, because this is more positive than this, the cross is positive than this, current will flow this way, and then through the it will again flow down, and then now you have to take it back. So how to take it back? I put another diode, and I have drawn it badly. This. So now the current basically through the load and then back through that diode goes there, right. So the current direction will be basically the end of zigzag. So essentially what you have done is that you have made a full wave rectifier but you don't have a center tap transformer. Instead, you are using this connection of 4 diodes. But this is not the way in which you might have got confused the way I've drawn it here. I want to draw it in a slightly more instructive and then motivate the circuit there. So let me just number these diodes. Let me call this as D1 and D2, right? And let me call this as 3 and that as D4. Okay. Then you might have seen this version of this circuit, and you might also even come up with a name for this, right? So let me say I have and I have 4 points. Okay. I'm drawing it in a very circular, right? A diode like that, come to that point, okay, and have a load which connected. So that is basically your resistor and capacitor. So the current then for the positive half cycle will flow like this through diode, that's your D1, right? It will go through the load, come back like that, and what should happen? Another diode. It's the same circuit I am drawing, right? It will be D, but I am just drawing it in a slightly different way. So that's here, connected here. Okay, so that diode is D2, and one can close this circuit. Can you see how this thing will close? Where the 2 diodes come in the other 2 arms of that parallelogram, and how will they appear? Will the anode or cathode come this side? Just think about it. Oh, I drew it. Okay, is this going to be D3 or D4? Think again. This is D. That is your 3, right? Can you tell me how this diode will appear? Will the anode or cathode come? Anode, right? And that would be D. So in the negative side, what would happen? Current will flow through this, through D3, then through that way, come through here, flow through D1 and back in here. Okay. And how do the output waveforms of the look? Same as, right? So just for completeness, right, and then remove that C and all of that. So basically that would be the final output wave across the capacitor. All right. So with this, basically maybe I'll just give a problem. Think about how you will design this problem. So let me say that I want okay. So let me say I 15 DC power supply, okay, with a maximum current of say 100 milliamps, okay, and V peak ripple of 1 volt. Use a full wave center tap transformer, and B what's called a bridge rectifier. So I forgot to mention that this circuit here is referred to as the bridge rectifier. You will see this kind of connection, like this. Why the reason I drew it this way, with 4 diodes along 4 sides of this bus, right, is because that connection is typically referred to as a bridge connection. Okay. You might cross a Wheatstone's bridge, right? So Wheatstone's bridge, what does it have? So the bridge. Right. So just for those who don't know about a bridge, just an aside, and then goes. What is the Wheat's bridge used? Where do you do this? Done it in physics lab, right? Yes. So basically you have 4 diodes connected this way, and what do you have? What do you have here? Here you have a voltage source, right? And basically here you have a galvanometer. So galvanometer is drawn with that arrow to an angle, right? It's not a source. Source will have the arrow either horizontal or vertical, right? So this is a galvanometer, and basically you will know 3 of these instances: R1, R2, R3, and then in one of the arms you put your unknown resistor Rx, and the condition for operation of this circuit. What happened in that situation? So when R by R is equal to R2 by Rx, current through galvanometer is 0. Okay, so that's it. All right. So you do this. In the next class, we will quickly look at the